For people who were away today, I wanted to go through the handout that I had left for you yesterday to work on for homework, talking about modeling with similar triangles. Hopefully you recognize that triangle ABC and triangle XYZ are actually similar. If you do comparisons of the XZ, so XZ is your longest side to the longest side, which is AC, you get a ratio of 3. Now you could flip those over and do the AC compared to the XZ and get a ratio of 1/3. Similarly, we could replace or compare the XY with the AB and get a ratio of 12/4, which is 3, and get a ratio again of 3. So our side lengths are proportional. If I compare the ratio of one set of sides to the ratio of another set of sides to the ratio of the third set of sides, we know that they're all equal, and therefore my triangles are similar through side-side-side similarity. Likewise, triangle GHI is also similar to the above triangles. If you look at AB compared to GHI, we're really looking at one being twice, side lengths being twice as long. So the ratio of GH compared to AB is a 2, GI divided by AC is a 2, and HI divided by BC is a 2 as well. So those side lengths are proportional, and these triangles are similar by side-side-side similarity. Now, when we look at the next question, it says how many times longer are the sides of each triangle compared to triangle ABC? So the sides of triangle GHI are 2 times longer than the sides of triangle ABC. So we're just taking like 4 times 2 to get 8. We're taking 5 times the 2 to get 10, and we're taking 3 times 2 to get 6. And then our other pair of triangles, these are 3 times greater over here compared to the original triangle ABC. It's possible when you did these, you would have put triangle ABC on the top for both of these. If you did, this would just become a 1/3, a 1/3, and a 1/3. It's just going to flip those ratios over. Likewise with this, if you put triangle AB on the top and GH on the bottom, you're going to end up flipping this ratio. So you're going to actually get a 1/2. Just remember, these guys really are out of 1. So when you flip it over, it's going to become 1/2. And they're still equal. They're still going to be 1/2 equal 1/2 equal 1/2. All right. So we know that this comparison 2 and 3 exists. What that means, these numbers here, the 2 and the 3, these are called the scale factors or scale ratio. Scale factor or scale ratio. So add that into your note. What that means is that's the number I'm timesing the lengths of one side of the triangle by in order to get our other triangle. So when you calculate a perimeter, I'm hoping you got 12, 24, and 36. What I want you to look at is the connection here. Really, if I take the 12 and times it by 2, we're going to get the 24. And notice that that triangle GHI was 2 times longer. What we talked about today is each one of the numbers 6, 8, and 10 could be factored by 2. So I'm going to pull a common factor out. That's going to give me a 3 plus a 4 plus a 5. And do you see that's really 2 times this, and this piece here is really the perimeter of triangle ABC. 3 plus 4 plus 5 was the perimeter of triangle ABC. So it's really 2 times as big as the perimeter of triangle ABC. If I look over here, I've got each one of these numbers being divisible by 3. I could common factor 3 out, and I have 3 times 3 plus 4 plus 5. And again, you can see that we're really doing 3 times the perimeter of triangle ABC. So this piece here again is our perimeter of triangle ABC. Okay, so our scale factor, this, if you notice, is really the 12 centimeters times by 3 to get the 36. So our perimeter is directly related to the scale factor. The perimeter of the one triangle would be the scale factor times the smallest triangle's perimeter. Now, is the same true for our area? Our area is base times height divided by 2. And I didn't mark this on our diagrams, but these were meant to have right angles in here. And they have right angles. If you try Pythagorean theorem, the Pythagorean theorem will be true for this. If I do 4 squared plus 3 squared, I do get 5 squared. 12 squared plus 9 squared does give me 15 squared, and 6 squared plus 8 squared will give me 10 squared. Looking at this time I'm not just taking the area and timesing it by 2 to get this area. I'm actually timesing by 4 to get this. And similarly, I'm not just doing 6 times 3 to get 54. If I do work backwards and divide, 54 divided by the 6 gives me 9, so I'd be taking 6 and timesing it by 9 to get 54. Now what we had noticed in class is 4 really is 2 squared, and 9 really is 3 squared. And when I asked why we would be having 4 and 9, and people pointed out, well, that's just 2 squared and 3 squared, I said, well, why are we squaring those? And a student, Amy, came up with the fact that we're working with square units, so we need to double both. And if you think about how these fit together, the 6 was really the 3 doubled. So 6 is the same thing as 3 times 2. That's the 6. And the 8 is really 4 doubled, or 4 times 2. So that really, I can do 3 times 2 times 4 times 2, or I could mix up my order here, and I could really say that that's the same thing as 2 times 2 times 3 times 4, all divided by 2. This piece here, the 3 times 4 divided by 2, is the area here. Do you notice that there's the 4 right here? So that's really 4 times the area of triangle ABC. All right. Likewise, our 9 was really 3 times side length 3, and our 12 really was 3 times side length 4. Rewriting that, I could write that as the 3 times 3 times 3 times 4, all divided by 2. This piece here, again, 3 times 4 divided by 2 is this calculation, and I've tripled one side, tripled the other side to make a total of 9 times my area of triangle ABC. Okay, and then we talked about cubics if we were going into 3-dimensional objects, and we had a scale factor of 2. This was 2 squared because it's area, it's length times width. With volume, we're looking at cubic units. So we have a length times a width times a height. When we calculate volume, if the scale factor is a 2, we're going to increase by 2 times 2 times 2, or a factor of 8. 2 cubed would be 8. If our scale factor was a 3, and we're looking at volume, we'd be increasing each dimension by a factor of 3, or 3 by 3 by 3, or 3 cubed, which is 27. So we kind of talked about that connection as well. All right, moving on to the next side. I know you guys have taken up, or have worked through this. Key ideas, I have those posted on my other notability thing, so I want you to make sure you get your key ideas down. One being that the scale factor is just the number that you multiply every side by in one triangle to get the sides of the other triangle, or it could be divide. The perimeter is just going to be directly related to the scale factor, and then the area will be the square of the scale factor, directly related. All right, we talked about why these triangles are similar. They're both at a 90-degree angle to the ground, so there's your one set of angles. And if the sun is way, way up in the sky, and its rays are coming down, it hits the top of the tree, and then the tree blocks the sun, and that creates the shadow here. If these guys are pretty close together, because the sun is so far away, the angle that the rays are making with the ground will be the same angle. Now, if we're talking about the tree here in Ontario and Hugo's out in Vancouver, that's not going to be true anymore. These are not going to be similar triangles, because that's quite a significant distance away. But as long as we're in the same close proximity, this is going to work for us. So they are similar by angle-angle similarity. Again, that's on notability. And how tall is the tree? Now, Hugo's 1.6 meters tall, and his shadow was 4.8 meters long. The tree, we're trying to find its height, and its shadow was 75 meters long. All right, there's different ways we can do this. We can calculate a scale factor here. So some people were doing this question this way. Scale factor would equal 75 divided by 4.8, and you get an answer. So that's what we're going to times the 4.8 by to get the 75, times by that scale factor, whatever that is. Then we would take Hugo's height, so the tree height would equal that scale factor times the 1.6. Okay, and I think in the end we got 12 meters for the height of the tree. Oops, I put that in the wrong spot, by the way. That should have all gone down here under how tall is the tree. This is the triangles being similar. All right, the nearby hydro pole, its shadow, so we're going to have it casting a shadow, and its shadow is 36 meters long. Okay, so this is our hydro pole. I'm going to put P for pole, and it's 36 meters long. Again, we still have Hugo and his shadow, 4.8 meters and a 1.6 here. We could figure out our scale factor. Okay, and do 36 divided by 4.8 and get that answer. And then we can take the pole height would equal whatever this scale factor is times the 1.6 Hugo's height, and that could give us our height of our pole. I want to show you another way you can set that up using the proportions. So I'll fit that into this space with the tree. If you look at corresponding sides, I know Hugo's height is the vertical here, so that 1.6 would match up with the height of the tree, could be compared to the height of the tree. And then Hugo's shadow, so Hugo's information I have on the top would be matched up with the shadow of the tree. All right, and then we could solve using proportion. So I have a ratio or a fraction equal to a fraction, that's called a proportion. So what we have, I have a choice here. I could cross multiply. I could use a property of proportion and flip both of these over and make that h over 1.6 equals 75 divided by 4.8. And then to get h by itself, I could times by 1.6 on both sides. And h will equal whatever that calculation is. Now either this was 12 or this was 12. I just don't have my solutions in front of me, nor do I have my calculator in front of me, but that's how you do that.